One of the important applications for the Fourier series expansion is to solve the PDE problem. This technique was developed by the Fourier works in order to solve the heat equation problem. In the heat equation problem, we can use the partial differential equation to model the temperature change of the heater rod with respect to time, where the U symbol here indicates the temperature distribution on this rod. Not only we want to know the temperature change with respect to time, we want to know the temperature change with respect to location in x-axis. The dimension of this rod is given, the length is from 0 to pi. From this graph, you have the y-axis to be the temperature and then your x-axis to be the dimension x. The initial condition is given here. At t equal to 0, the rod is heated at 100 degrees Celsius at all the locations. When t is greater than 0, we give the boundary condition to the rod, where we put some cooling stuff to ensure the temperature at the ends here is equal to 0 degrees Celsius. So when t is greater than 0, you should expect at these two corners here, the temperature will be equal to 0. For example, at the center point here, which is equal to pi over 2, approximate to 1.6 here, you can see that the temperature drops over the time. And the temperature drops faster when it's close to the cooling source. The data present in this graph is the temperature change with respect to the space in the dimension x and in terms of time. Let's assume that this data is actual data which is obtained by the experimental work. Many engineers and scientists are trying hard to solve this PDE problem in order to obtain the solution for the heat equation problem here. However, most of them only able to obtain this temperature distribution solution in the general PDE solution format. However, this solution is less useful because there is unknown coefficient here. We need to find the answer for the coefficient here in order to obtain the particular PDE solution. Particular PDE solution is more meaningful in many engineering applications. For example, in this case, by having the particular PDE solution, then you can model and predict the temperature distribution of the heater rod with high accuracy as compared to the actual experimental data. Fourier is the first guy who solved this problem by applying the Fourier series expansion. By applying the initial condition, which is at t equal to 0, the temperature at all the x locations is equal to 100 degrees Celsius. So this information is given here. So substitute the t equal to 0 into the general PDE solution here. Exponential 0, you obtain 1. Then you have the summation from n1 to infinity, and in the bracket of the coefficient b multiplied with the sign term. Many engineers and scientists were having problems to solve the unknown coefficient b here from this equation. Fourier had developed the Fourier series expansion method in order to solve this coefficient. You have learned the half-range Fourier sine series expansion, half-range Fourier cosine series expansion, as well as the full-range Fourier series expansion. If you look at this component, with the summation of the sign term here, and the x value is given within a finite interval, which is from 0 to pi here. So this is the range for the x value. Then you should be able to link to the half-range Fourier sine series expansion formula that you have learned previously. In this formula, when you have a function which is equal to the summation of the sign term, then the coefficient here will be equal to this formula. When you compare to the right hand side, then this will be your ux function, and your ux is equal to 100. Tau is the finite interval, which is equal to the pi here. For the half-range expansion, P divided by 2, which is the half-range of the period, will be equal to the tau. And substitute the value for tau, you have pi here. So the period is equal to 2 pi. Omega is equal to 2 pi divided by P. Substitute inside, you should obtain omega equal to 1. Therefore, you can see n omega x formula, you have your omega equal to 1 here. Therefore, the omega here can be substituted by 1. And then L here is the half period. So 1 period is 2 pi, half period L will be period divided by 2. Therefore, is equal to pi. So far you have obtained the half-range Fourier sine series expansion formula to be this. And then you success to obtain the parameter for this formula. So you have the ux here equal to 100. And then you have the omega equal to 1 here. And you have the tau equal to pi. Lastly, you have the half period L equal to pi as well. So we are going to solve this integration. Integrate sine nx, you obtain negative cos nx divided by coefficient inside, which is n. 100 multiplied with 2, you obtain 200 divided by pi. Substitute the limit inside, you have the cos n pi. And then substitute 0 inside, you have negative cos 0, which is equal to negative 1. Then you know cos n pi is equal to negative 1 power of n. Negative here become positive. Therefore, you have 1 minus with negative 1 power of n. So this is the answer for the B. Substitute the B inside the general PDE solution that you obtained previously. Then you can obtain the particular PDE solution here. This solution is very useful as it can be used to determine and estimate the temperature change with respect to the time as well as different location x. When you plot the graph for this solution, then you should obtain at t equal to 0, all the point here has temperature equal to 100 degrees Celsius. At t equal to 1, which is this, then this is the temperature distribution from the point 0 to pi here. At t equal to 1.5, you have the temperature distribution in the green line here. And you can continue and estimate how much time it takes to reach the steady state temperature here, which is equal to 0 degrees Celsius. Same with the boundary condition. So you see the Fourier series expansion is very useful to obtain the particular solution for the PDE problem. Make sure you master this technique because you are going to use it to solve the PDE problem later.